Hello, everyone. We are the Thin Impact Resistant Work Gloves group. My name is Colin Brannigan, and my partners for this project are Jürgen Homeyer, Luke Lofel, Paxton Smith, and Ali Zetub. The goal of this experiment was to create a material for modern work gloves. Current work gloves are either flexible or durable, but rarely both. The team wanted to create a material that would compete with current durable work gloves in terms of protection while maintaining a high level of dexterity for detailed work. There's a clear opening in the work glove market, and this project has the potential to improve safety and functionality for workers. The key question of this project was, how do we develop a material to be used in a glove that offers impact resistance without hindering the dexterity of the user? The objective was to test several material variations to find the optimal configuration to resist damage. We made our material samples using Kevlar fabric, 1200 grit silicon carbide powder, polyethylene glycol 3550, and ethanol. The silicon carbide powder, polyethylene glycol, and ethanol were mixed in different ratios to produce various shear thickening fluids, or STFs. These non-Newtonian fluids increase in viscosity when exposed to shear stress, improving the impact and puncture resistance while remaining dexterous under normal usage. The technology has been applied to body armor in the past and has the potential for use in other fields. We used each STF variation to saturate the Kevlar sheets to make sample materials. We then tested these materials in a puncture test to determine the forces at which they failed. The group initially had slightly different intentions for this project, and after conducting our first set of experiments, we were not satisfied with the results. We went back and redesigned our experimental process to provide more meaningful analysis and results. Additionally, we swapped our fabric from woven fiberglass to Kevlar due to the failure of the first material. Our testing method was inspired by the American Society for Testing of Materials, or ASTM. Specifically, the ASTM F1342 procedure for testing protective clothing material resistance to puncture was used. We also studied several academic articles that influenced our selection of materials. Our experiment differs from those already conducted by the ASTM because the STFs we used were different, as well as some of the testing methods that we employed.
Our test plan involved creating different shear thickening fluid (STF) mixtures with varying silica content by weight. These mixtures were then diluted using ethanol before Kevlar sheets were soaked to impregnate them with the STF. Finally, puncture tests were performed to determine the force required to puncture a single or double layer of STF-saturated Kevlar sheet. The displayed figure shows a simplified experimental diagram. The setup we used was based on ASTM puncture testing standards with modifications for the equipment that we had available. Our setup included a drill press, puncture needle, support assembly, and an S-type load cell for force measurement. The experimental conditions tested were varying levels of silica by percent weight in the STF mixture, which was then used to saturate the Kevlar sheets. Tests were conducted for neat sheets, our control sample, as well as 10, 15, 20, and 40% weight silica STF saturated sheets. For each set, 3 trials were performed using a single sheet and 3 trials were performed using 2 layers of Kevlar sheets. To perform puncture tests on the Kevlar samples, a 30 kilogram S-type load cell manufactured by CALT was used in conjunction with a finishing nail as our puncture needle, an Arduino Uno R3 with a SparkFun load cell amplifier to capture measurements from the load cell, and a Delta drill press for vertical translation of the needle. The specimen support plates were 3D printed in PLA and secured using 1/4-inch carriage bolts. The puncture test used in the project was based on the ASTM standard test method for protective clothing material resistance to puncture, albeit with a number of modifications for simplicity and due to the equipment we had available. In terms of relevant calibration, the load cell and HX711 board required calibration between each trial, which was accomplished by using a known weight to adjust the gain factor on the HX711. The first step in the experimental process was to create the shear thickening fluid-saturated Kevlar sheets. This was done using polyethylene glycol, or PEG, mixed with silica powder. This STF was then diluted with ethanol in a 3-to-1 ratio to assist in impregnating the sheets with the STF. After soaking each sample for 1 minute, they were all air-dried for 4 hours. The second step in the process was to puncture each set of samples, which was accomplished by placing a sample in the specimen support assembly fixture shown on the right, securing it, and performing the puncture test. However, before each test, as mentioned previously, the CALT load cell was calibrated with a known weight, and the HX711 board gain was set due to the heavy fixture modification between tests.
The schedule of the team became fairly hectic in the last month due to the reworking of our initial test plan towards the end of the semester. We worked to restructure our testing method as well as transition from using fiberglass sheets to using Kevlar sheets. Fortunately, most of the materials were either already owned by the team members or purchased at the beginning of the semester. The following purchases were made for this project: one CALT load cell for $38, one SparkFun HX711 load cell amplifier for $10.95, 7-ounce weight Kevlar for $17.95, 1200 grit silicon carbide powder for $9.80, and polyethylene glycol 3350, also known as Miralax, for $9.99. The risk assessment from the team was conducted at the beginning of the semester and did not change despite the restructuring of the experimental methods. There were 2 primary risks in this project. The first were the physical dangers of conducting a puncture test by using tools and machinery. To alleviate this, the team agreed to have only one person operate any tools at a single time, while the others looked for possible hazards. The more pressing hazard was the 1200 grit silicon carbide powder, which is a fine dust. If we were not careful, the dust could easily be inhaled, causing irritation and possible lung complications. The team used KN95 masks at any time the silicon carbide powder was used to alleviate this risk. We tested 10 different material configurations 3 times each, totaling to 30 separate trials. Each trial lasted up to 20 seconds and recorded between hundreds to thousands of mass readings in intervals of milliseconds. The table on the left shows the maximum load acting on the Kevlar in each of these trials. Immediately after the material was punctured, a load was no longer applied. The figure on the right shows the average maximum puncture force of each material configuration in newtons. There is not a strong connection between the amount of silicon carbide powder and the maximum puncture resistance of the material. As expected, every double sheet configuration of the material performed better than its single sheet configuration, while the 15% and 40% silicon carbide powder configurations of the material do perform marginally better than the other configurations. The results are not entirely conclusive. However, we believe that this slightly positive trend warrants further investigation into this technology. Possible sources of error are the production process of the material samples, as well as the point used for the puncture apparatus. In future iterations, a 2 mm rounded tip needle made of a stronger material is suggested. The slightly positive trend of points shows the possible viability of this technology and warrants deeper exploration in the future. The results of this experiment provided a slight positive trend that showed the possibility of this technology being viable, but they were not conclusive. There are multiple possible sources of error that influenced these results. Primarily, the variations between the referenced ASTM F1342 testing method and the actual testing method we used may have been a cause of error. ASTM recommended a 2.03 mm rounded tip for the puncture apparatus, but we used a finishing nail instead. We tried to follow their recommendation by 3D printing the rounded tip, but the PLA filament could not withstand the loads and the 3D printed puncture needle failed. In the future, the team would use a stronger material for the puncture apparatus needle so that proper geometry recommendations could be adhered to. Additionally, the team recommends further research into the production method of the sample material. Different fabric materials and combinations of shear thickening fluids would greatly broaden the possibilities of a thin impact resistant glove material. Thin impact resistant glove material has lots of potential as a technology. There's still a huge number of combinations of different STFs and fabric that we have not investigated. The future steps for this project would be to iterate and improve the testing apparatus and broaden the range of materials that we experiment with. We learned a lot about material science and conducting an experiment from the ground up in this project. However, one of the most valuable things we learned was how to adapt when things don't go as planned, while keeping the initial goal in mind. We would like to thank Professor Carl Hoover and Muhammad Ali Raza for providing guidance in this project. Thank you.